As an example of applying Faraday's law, we'll look at what is called a sliding rail problem. And it's formulated in various ways, but it's a very common application, at least to display Faraday's law. The idea is one has this rail here, so it's an exposed metal rail on the top, a wire connecting them with a resistive element here, a resistor, and then another rail here. So the top and the bottom are exposed metal rails, and then we lay across it a metal sliding piece, slider. Again, it's metal, and so we make metallic contact, and we have the potential anyway of having a circuit over here in this portion. Some geometry, I gave it this width of this, and then this distance from this edge to where the rail is x, and we're going to be moving this rail at constant velocity v0 outward. Yeah? And as a result, x is a function of time. Well, in general, I could use the kinematics formula. There's no acceleration, so there's no acceleration term. And so x as a function of time is x0 plus v0 t. And then I apply a uniform magnetic field throughout this region. Excuse me. And as shown here. And then pretty obviously, as this rail moves outward, more and more of these field lines are going to come inside, and by Faraday's law, that's going to induce an EMF and induce a current. We can use Lenz's law to determine what direction the induced current will be. The current is, as I pull this in, as I pull this out, I'm going to getting more field lines. So I need to have a current flow so that it produces a magnetic field that cuts through the center in the direction opposite to those. So it will cancel out these that it gets drug across. And if you look at that, apply the right hand rule. There's really only two directions to check, but looking at the top, grab that wire, thumb pointing in the toward the left, and then in between, or in the enclosed area of the loop, your fingers will curl up out of the page, and so as we drag in this one, it'll induce a field line over here that comes out of the page, and so those will tend to cancel. You can do the same analysis down here, but in any event, the current flow is in this counterclockwise direction when viewed from the top, that's induced in this circuit up here. So Lenz's law gives us that direction. Again, usually I just check both directions to see which one will either add or subtract a field line depending on what the situation is to cancel out the addition or subtraction of lines caused by some other process. This is one where I've got a nice planar area that's enclosed. I've got a nice uniform field. And so to count the field lines, that's just the magnetic flux cutting through this is a B dot A vector. Or again, the scalar product is the magnitude of B, which is B naught, the magnitude of A, times the cosine of the angle between the two. I chose the normal to the area, and I do this a lot too, just to keep from carrying around a negative sign. I chose the normal to the area going into the page, so it's going in the same direction. Remember, area vectors have normal n-hats, so I chose n-hat going into the page, and so this dot product, the cosine is 0 degrees. And that's just so that I get the magnetic flux is B naught A, which effectively counts the number of field lines that's cutting this. This is an example. If you look at this, there's really three ways you can change this magnetic flux. One is if the magnetic field magnitude is a function of time, well, in this case it's uniform and constant, so it doesn't change. I could change the angle between B and A vector, but they're both in the same direction all the time. And so that one doesn't change. And in this one, though, what does change is you pull this out with constant speed V naught is the area enclosed changes. So this is a case where the number of field lines changes because the area, in this case, is increasing in a constant field at a constant angle. The area, well, it's pretty easy. It's just the length times the width, and that just is Wx of t. So that tells you how the magnetic flux changes with time. And the induced EMF is just d phi b dt. Again, in magnitude, B naught and W are constants. I can pull them out, and so it simply becomes the derivative of x with respect to time. But we know what that is. It's wherever it started plus the speed, the constant speed we're pulling it out with, times t. And we get the induced EMF magnitude is of this form, and it's in such a direction as to produce a current going in this direction. The direction of the EMF. Well, if you think about this, I've got an analogous. I've got a resistor, I've got an induced current, and there's an induced EMF. Remember, current always flows from positive down to negative, and so if I were drawing in an induced EMF here, I could put a little battery symbol. I don't like to do that usually, but one could do that, and you sometimes see that. But in any event, the EMF around that whole closed loop by Kirchhoff's voltage loop rule is just I times R. And as a result, the induced EMF is the induced current. There's current flowing in that loop times that resistor. Again, I'm assuming that there is no resistance lost in the rails or in this the slider. They're essentially zero resistance compared to this resistor that I've got right here. But EMF is this. Around the closed loop, the total EMF is the current, induced current times the R. This is the induced EMF. And so the induced current is E over R, but we just computed the induced EMF was B naught W V naught. And so plug that in for E, and you get the induced current. This is a nice expression. We can get the electrical power that's dissipated in that resistor. In general, the power in a resistor is I squared R, if you remember. In our case, the current going through it is the induced current, which is this expression up here. And so I get that the power that's essentially delivered to this resistor is being used by that resistor is the time you simplify things and get rid of one of the R's is this expression in terms of how fast we're pulling it out, the applied field, and then, of course, the resistance there. Now, you might do this kind of a situation. Ordinarily, that power is going into this resistor, and for a common resistor, it might just heat it up and get hotter. But you could think of this resistor as being the filament in a light bulb. In which case, as you're pulling this out, this current would go through the filament of the light bulb, and the light bulb would begin to glow. And Faraday did demonstrations to people more or less like this arrangement, and got actually quite a reputation of going around England and Scotland. Faraday was Scottish. And giving his electrical demonstrations that show these effects to sort of publicize this work. And people are just interested in generally these kinds of things, I think, is sort of a traveling show. and got so famous, in fact, for it that he was invited to Parliament to give his show to them, which he did. He showed them this sliding rail with a little filament that could glow, and I think he knew immediately what he had here. He had a way to make something, a glowing element that might someday replace the candle with the currents. And but the the Parliament was very nice, and they applauded after he gave his demonstrations and talked about this. He gave other aspects of it too. As I said, he was primarily famous for his chemistry of candles. And one of the questions they opened up after his presentation and his demonstration show, opened up to questions from members of Parliament, and one of the parliamentary members asked him, said, "Well, Professor Faraday, this is all well and good, but what possible practical use could any of this have? This is just parlor tricks." And Faraday by that time was, I guess, feeling comfortable enough that he could. And I don't think the Scottish ever particularly liked the British anyway. But he said, "Well," he said, "Sir, I don't know," is the recorded response. I said, "I don't know what practical use it will ultimately have. Says, but I can readily assure you that someday people like you will tax it." And sure enough, nowadays you buy electricity and have lights. Well, there's a tax associated with the electricity. There's a tax associated with the light bulbs, etc., that are used. So Faraday's prediction actually came true. Well, we can look at it from other perspectives, not just electrical. But if you remember here, I've got a current flowing, particularly on this rail. I've got current everywhere, but on the rail, I've got current flowing in this direction, the induced current, but it's in a magnetic field. And I know that current carrying wires in magnetic fields have a force on them. And if you look at the force on this, the magnetic force is going inward into the interior. And I've drawn that, I think, down here. The wire going up, induced current, magnetic field. You use I, L vector across B naught. And the angle between them is 90 degrees. B is into the page. L vector is up in that length. And therefore the angle between them is 90, and so this becomes I, L, B naught, sine of 90. And the current is the induced current. Well, we had the expression for that above. The length, well, it was really, if you look at it, the length of this is really the length W. So I plug in W. And B naught, of course, we had. And if you multiply this out, you get that there's a magnetic force opposing the motion of this magnitude, going backward, going to the left. But remember, we're pulling this with constant velocity. And a constant velocity, an object at rest or in uniform motion, the sum of the forces are equal to 0. And so if I'm moving at constant velocity, the sum of the forces, well, there's two forces. There's the magnetic force that tends to want to slow it down, but I'm having to pull it so that the velocity is constant, and I'm pulling it with this applied force here. So it has to be equal and opposite to it to maintain constant velocity. And so we could look at the mechanical power that's being supplied. Remember, power is also dW dt, and the power being supplied by the applied force will work as force through distance. So infinitesimal distance dx gives an infinitesimal amount of work times the force times dx. But dx dt is just the velocity. And so I get the applied force times the velocity. It gives me the power that's being supplied to keep it moving at constant velocity. I've got the force. That's in this direction because I have to apply an equal and opposite magnitude force to the magnetic field. So the force I have to apply has to be of this magnitude. That's F that I'm applying, and the speed I want to keep it going at is V naught. And so you get the power supplied by me pulling it is this expression. But if you look at that, that's exactly the same expression. That's the power that's being used by that resistor. One is really the power being supplied. One is the power being used by that resistor, or if it's a light bulb element and going into producing light. So there's conservation of energy on a per time basis, and the power in is going in is going to be used by something, and it goes into increasing the illumination or increasing the heat if it's just a regular resistor. Well, that's the sliding rail problem and demonstration of Faraday.